And I think I can share my screen. Okay, so very good. So we saw last time that in the irreducible representations that we found, I mean the structure was very nice. I mean we could kind of represent it using a graph, represent the action using a graph, and we noticed that the element H, so that's that diagonal matrix with entries 1 and -1, would act on all of these representations with eigenvalues. So we would act diagonally on these representations. We always found a basis for which the action was diagonal, and the eigenvalues were very nice because they're integers. They were symmetrically displaced, so we would start with a positive non-negative integer m, and then go down 2 by 2 and up to the integer minus m. So it was very symmetrical, and so it makes sense to start looking at these eigenspaces in general. So given any module, even if it's I'm going to focus today on finite dimensional modules, but even if the module is infinite dimensional, I can look at the eigenspace for H on that module. So the vectors in M on which H acts as multiplication by a given scalar. So in this definition here, mu, so this is the notation that I'm going to use, is the mu eigenspace for the action of H on the module M. This can be 0 or it can be non-zero. There might be eigenvectors or there might not be eigenvectors, okay? And traditionally we call this a weight space, okay? We think of these eigenvalues as weights, okay? So this is it, okay? And you notice that, I mean, so in the representations that we constructed, we could always break up or you know, find a basis for the representation in which the action was diagonalizable. So that representation would be a sum, a direct sum of its weight spaces. So the weight spaces are not submodules because I mean, these modules are irreducible, but they're invariant under just the action of H, okay? And this action was diagonalizable. We also noticed that, I mean, if you remember, if I started with the largest eigenvalue, so remember I chose to denote these modules by Lm, where m was the largest eigenvalue for H. Okay, and then we started here with this eigenvector where H acted with eigenvalue m, and then f would be going down the module like this. Okay, and then the eigenvalues would reduce by 2. Okay. And this is no coincidence. We're going to see that this will always be the case. So so what we're going to show is this. So if I have an eigenspace for the action of H with eigenvalue mu, and I act on it on this eigenspace by E, then I end up in the eigenspace of weight mu plus 2. Okay, and so E adds 2 to the eigenvalue, F subtracts 2 to the eigenvalue, and of course, H just acts as multiplication, so it respects these eigenspaces, okay? And this is very easy to do, but it's just a standard trick in Lie theory. So let's take some element M in M mu, and let's act on it by E. And I want to see if this happens to be, if I'm lucky that this is an eigenvalue for H or not, and if it is, what is an eigenvector, sorry, for H or not, and if it is, what's the eigenvalue? So the way to find out is to act on this element by H and to see if the result is a multiple of E times M and what this multiple is. Okay, so, well, what can I do here? Remember that I told you that, I mean, if I thought of the matrices affording this representation, these matrices, so for example, E H minus H E was equal to 2E to replicate the relations in the Lie algebra. Okay, so using this, I see that HE acting on the element M, it's here, is the same as changing the order, so EH plus, if you want, adding the bracket of H and E acting on M. And this bracket of H with E is precisely 2E. Okay, so this just follows from this relation, but this is a better conceptual way of thinking about this. Okay, I can change the order of the action if I compensate by adding the commutator of the two things that I'm interchanging. Okay, so if we do this, we see that, well, by hypothesis, H acting on M is just mu times M, and the bracket of H and E, this is one of the famous relations, that's 2E. Okay, so this is a linear action, so the scalar mu can come outside. So this is going to be just mu plus 2 multiplied by EM. So I've just shown that if I take a vector here and I act on it by E, then this new vector will be an eigenvector for H with eigenvalue mu plus 2, so it is in the space. Okay, and the other relations, the other relation with F is proved the same way. Okay, so this is very nice. Okay, and with this, we're able to kind of get a breakthrough. So what we're going to see here is true for essentially any simple finite dimensional Lie algebra. So it's not just a very small example with this Lie algebra SL2. This will work in general, but here I'm just focused on SL2, and it's the following. So imagine you have a finite dimensional module, any non-zero finite dimensional module. My first claim is that there will be some eigenvector for the action of H. So there's going to be some eigenspace here, m lambda, and some scalar lambda, on which H will act as multiplication by lambda, a non-zero vector with this property, and with the additional property that this vector is killed by E. Remember that this was always the case in our simple representations that we found. The vector on the right was always killed by E because E was moving to the right and it couldn't move anymore to the right, so it was killing that right-hand vector. And we're going to show that this will always be the case. And moreover, and quite surprisingly, we're going to show that, I mean, you might have thought that that the scalar lambda could be completely arbitrary, but I'm going to show that given that eigenvector with eigenvalue lambda, I'm going to show you that lambda is in fact a non-negative integer, and that this vector here, this eigenvector killed by E, in fact will generate a submodule isomorphic to the simple module that we had already constructed. Okay, so this seems kind of a lot, right? It seems surprising to be able to prove all of this, but we'll see. It's not very difficult. Okay, and it's very typical of an argument that one would do in the representation of Lie algebras. Okay, so let's start. First of all, can I guarantee the existence of an eigenvector for H? The answer is yes, because the field is algebraically closed. I'm assuming the field to be algebraically closed, if I haven't said that before. So since the field is algebraically closed and H is acting as some kind of an endomorphism of a finite dimensional vector space, there will be an eigenvalue. Okay, so I just pick for now just so that part is granted. So I know that there exists some scalar mu. It's not exactly the scalar that I need necessarily, and there exists some non-zero element W. Such that, well, I'm repeating what's already written here, but it's worth repeating, such that when I act by H on this element W, I get mu times W. And this is just because since the field is algebraically closed and the representation is finite dimensional, there has to be an eigenvalue. So there's a characteristic polynomial, and the characteristic polynomial of the endomorphism induced by H must have a root. And so this is guaranteed, okay? But the point now is that for now I need to show that I have this simultaneously with the fact that assert that the vector is killed by E. Okay, and this is not necessarily true, now. Okay, well, what can I say? Well, I start with W, and then I can consider the vector E times W, and I can consider the vector E acting on E times W, and I can consider the vector E acting on E, acting on E, acting on W. You'll notice that I'm being careful because, I really wanted to say E cubed acting on W. The problem is E cubed does not exist in the Lie algebra. That's not the operation in the Lie algebra. Okay, but if I think of E as an endomorphism, then I could write E cubed. Okay, so often I will, because it's just simpler understanding that I'm not talking about, it's not E cubed in the Lie algebra, I'm talking about a representation and the endomorphism induced on this by this representation. Okay, so this is solved by a nice gadget called the enveloping algebra, but I'm not discussing this too much yet. Okay, so I start looking at these vectors, and what do I know? Well, this W is an eigenvector with eigenvalue mu. I just proved that this is an eigenvector with eigenvalue mu plus 2. This has eigenvalue mu plus 4. This has eigenvalue mu plus 6, and so forth. My field has characteristic 0. Okay, algebraically closed in the end, when we get complete structure theory for the representations, finite dimensional representations of SL2, we could, I'm not going to go into that, but we could, using a certain trick, get rid of the hypothesis that the field is algebraically closed, but we could not get rid of the hypothesis that the representation is finite dimensional. Okay, so and the hypothesis that the field has characteristic 0. Okay, so since the field has characteristic 0, all of these scalars are distinct. Okay, they're all distinct. But you know that eigenvectors corresponding to distinct eigenvalues will be linearly independent. So this would tell me that I would have here infinitely many or arbitrarily many finite linearly independent vectors, which cannot be because my module is finite dimensional. Okay, so where's the loophole? What's wrong here? Well, these elements are eigenvectors provided that they're not 0. What I really proved is that, for example, that this is in the space M mu plus 4. An eigenvector is a non-zero vector in this space. Okay, so I know that this element is in M mu plus 4. If it's non-zero, it's an eigenvector. If it's equal to 0, well, then it's equal to 0. And so my argument is just that, these vectors cannot all be non-zero, because if they're all non-zero, they're all eigenvectors with distinct eigenvalues, so they're linearly independent, and my module would have to be infinite dimensional. So in the end, what I know is that there's a point when this is going to be 0. Okay, so by what I said, there exists some power, let's say k, such that when I do e to the k acting on w, this is not 0, but if I do it one more time, this will be 0. Okay, so now I'm calling this vector v0. So it's a non-zero vector, and e acting on v0, that's ek plus 1w, and that's equal to 0. Okay, and moreover, this element v0 is in the eigenspace corresponding to the eigenvalue mu plus 2k, because I've acted with e k times. Okay, so this will be my lambda. So lambda is equal to mu plus 2k. So I've just produced a non-zero element, v0, okay, which is simultaneously an eigenvector for h and killed by the element e. Okay, so such an element, I didn't say this before, such an element is called a maximal vector. Okay, so a maximal vector is a non-zero element in your module, which is simultaneously an eigenvector for h and killed by e. Okay, so that's a maximal vector. So we just proved the existence of maximal vectors in finite dimensional modules. Okay, now I'm going to prove the surprising thing that in fact this lambda cannot just be any scalar. The fact that I have a maximal vector, so the fact that E kills this vector forces this lambda to in fact be an integer. Okay, a non-negative integer. So that's what I'm going to show next. And for that, I'm going to, well, this is not going to be the first thing that I'm going to show now, just to be a little bit economical with time. So let's start with this vector v. So remember, I have this vector v0 with the property that E times V0 is equal to 0, and H times V0 is equal to lambda times V0. Okay, and I'm going to be guided by what I already know about some of the representations of SL2, which is, remember this vector in the representations that I know, which are very particular because they're irreducible, and not every representation is going to be irreducible. But in the ones that I know, what I observed is that I start with such a vector, which is appearing on the right-hand side of my diagrams, on my graph diagrams, okay? And then I could obtain all of the other vectors by acting with f. Okay, so let's see what we can get doing this. So let's start with v0. Let me act with f several times. Let's see, I times. And let me call this vector vi. Okay, for the purpose of having nice formulas, I am just technically going to divide by I factorial. This is not important, but it's just so that you're going to see the same formulas that you saw before. Okay, so I'm defining these vectors for I greater than or equal to 0. Okay, so all of these vectors are in my module, obviously. And what do I know about the action on these vectors? So I know how H acts, H acting on Pi, because every time I act with f, I subtract 2 to the eigenvalue. Okay, so initially I had an eigenvalue of lambda, I act I times with f, so I subtract 2i. Okay, so this is going to be lambda minus 2i I. Okay, so excellent. I know how h acts on these vectors. Do I know how f acts on these vectors? So f acting on vi, that's 1 over I factorial f to the I plus 1 v0. Okay, well, what I'd really like, so that it looks like a basis vector, I would really like it to look like f to the I plus 1 divided by I plus 1 factorial. But so that the two things are the same, I need to multiply by I plus 1. And so this is just I plus 1 multiplied by v I plus 1. Okay, so f is moving one of these basis vectors to the next one and multiplying it by the scalar I plus 1. So far, this is really matching what we have for the simple representations that we've constructed. Okay, now the tricky part is to look at the action of E. Okay, so to look at the action of E, I would need to know how E acts on f to the I v0 divided by I factorial. Okay. So for this, I need a formula, which I have here, I think, on my next slide. Let me just copy it so that I can use it. I mean, this formula is very easy to prove by induction, but when we later look at this relate SL2 with generalized Weyl algebras, actually you'll see a way to come up with these formulas, in a very nice way, without having to guess too much. Okay, so I'm going to use this formula. So we've learned. Oops, sorry. So this is 1 over I factorial. I want to change the order of E, and sorry, for some reason my exponent of I ended up as an index. I don't know Why? Mysteries of life. So I want to interchange E and Fi because I don't know what E does to this Fi V0, but I know what E does to V0. Okay, so I'm going to change the order, that fundamental trick of Lie representation theory that I mentioned before. And I can do that at the expense of adding a commutator. Okay, so plus 1 over I factorial, the commutator of E with Fi. Okay. And then I can use the formula below because this first term here is equal to 0 because V0 is a maximal vector. And so using this formula that I have below here, so replacing, I guess, k by I minus 1, I get that this is going to be I f to the I minus 1 h minus I minus 1 acting on V0. Okay, if I didn't make a mistake. If I did, it won't be too serious. Well, one mistake is I already forgot to divide by I factorial. Okay. Now this I factorial with the I in the numerator they will cancel, so I'll get 1 over I minus 1 factorial f I minus 1. Now, how does H act on V0? H acts on V0 as lambda, right? So this is going to be lambda minus I minus 1 times V0. And lambda minus I minus 1 is just a scalar, so it can be moved outside. And what remains, you'll notice, is precisely the basis vector Vi minus 1. Okay, and this is true, well, technically, I don't need this formula anymore, I'm going to delete it to have a little bit more space. Technically, this would be true for every I greater than or equal to 1, okay? But what happens when I is equal to 0? E times V0 is equal to 0, by definition of V0. So if you want, this could be valid for all I greater than or equal to 0 if I define V minus 1 as 0. Then I'll have a nice formula. Okay, so you'll notice that this completely agrees with the action that we've seen for those simple modules, except that this lambda seems to be an arbitrary scalar. Okay, and in those simple modules, that lambda appearing was actually a non-negative integer. So how am I going to pull that out of the hat? Okay, well, it's already in here. It's just a matter of exploiting the formula that we already had. So this formula is saying, I'm going to repeat it here, that E acting on Vi is equal to lambda minus I minus 1, Vi minus 1 for all I greater than or equal to 0. Well, I know, remember, that well, it's not quite remember the argument that I used before, that at some point these vectors must be 0 because Vi, all the Vi have distinct eigenvalues. So V0 has eigenvalue lambda, V1 has eigenvalue lambda minus 2, V2 has eigenvalue lambda minus 4. We've done this argument. These eigenvalues are all distinct, so these vectors cannot be all non-zero. So there will be, let's say, M be such that f to the m v0 is still non-zero. I mean, this, for example, when m is equal to 0, this is certainly true. So let's push this as far as we can. And f to the m plus 1 v0 is equal to 0. Okay, there exists such an m, okay? And so I'm going to fix it, okay? So this really means that Vm is equal to 0, is non-zero, and Vm m plus 1 is equal to 0. Okay, so if Vm plus 1 is equal to 0, when I act on it by E, certainly I get 0, because E acting on 0 is 0. Okay, but if I use the formula that I just written up there, this should be equal to lambda minus m times Vm. But Vm is not 0. So how can a multiple of Vm be 0? Well, if the scalar is 0. Okay, so this forces lambda to be equal to m, which is a non-negative integer. So this is very, I mean, it's so simple, but it's so surprising. Okay, so we've just proved that this lambda cannot be arbitrary. It's a non-negative integer. And now looking at these formulas for the action, it's exactly the formulas that we got for the module Lm. Okay, so this V0 does generate a submodule isomorphic to Lm. Okay, so hope this is all fine with you. What made this work? So there are a few things that were important and a few things which were not. Okay, algebraically closed field. It was important because I needed first to have an eigenvector. Okay, sorry, an eigenvalue. Okay. So I used that hypothesis, but I mean, in the end, we're going to see that this eigenvalue is just a non-negative integer. Okay, and any field of characteristic 0 will have the non-negative integers. So the field, I mean, when we prove the whole theory, then we can go back and see that actually the field being algebraically closed is a hypothesis that can be removed from this theory. Okay. Characteristic 0, we used it in a very important way because, I mean, I used that to see that all those eigenvalues are distinct. Okay, and in fact, in fields of positive characteristic, this argument will fail, and you will have other kinds of modules where the action is kind of cyclic. Here, essentially, I've showed that the action of E and F is nilpotent. Okay, in positive characteristic, you can have kind of a cyclic action. You get to the very end, and instead of going to 0, you circle back and you go back to the beginning. So this was an important hypothesis. And finite dimensionality is certainly an important hypothesis. Where did I use it? To see that there couldn't be infinitely many eigenvectors. Okay, and in fact, if the module is not finite dimensional, I will not be able to prove this result. And in fact, there exist simple modules that look like this, but they're infinite dimensional, for which this lambda is not an integer. Okay, so this was a fundamental hypothesis. Okay, very good. So we've just proved this result here. There's a nice exercise here that, again, using when we see generalized Weyl algebras and when we relate them to this to sl₂, we'll see that such a formula is kind of easy to get to. As it is now, you can prove it by induction. It's a pain. Okay, since this is being recorded on YouTube, I'll stop here, but it's a pain to prove this. Okay, so we can capitalize now on what we've done because, I mean, an immediate corollary is that any finite dimensional simple sl₂ module must be one of those that we've seen before. Because if I have a finite sl₂ module, a finite dimensional simple sl₂ module, let's call it M, by what we've shown before, I know that there exists some element V0 in M, which generates some submodule isomorphic to Lm. Okay, so this, I mean, what we've shown already shows that any finite dimensional module, if it's non-zero, it must contain some Lm. But if on top of this it's simple, it has to be equal to Lm. Okay, so any simple, so we've already found all of the finite dimensional simple modules for sl₂. Okay, so this is a consequence of what we've done. So what can we be happy about? Well, we know all of the simple finite dimensional representations of sl₂. Let me give you a warning. sl₂ has a lot more simple representations, but those are infinite dimensional. Okay, and some of those infinite dimensional, some simple ones, I mean, a lot of you in the audience, I'm sure, know them. They're related to Verma modules. Okay, but they're more. Okay, there are more representations besides the Verma modules. There are also simple modules, which are infinite dimensional, which are not Verma modules, and those are called Whittaker modules. And there are still other types of modules. So if you want to know all of the simple representations of SL2, then you have to go much further than what we've done. This is known, although it's still quite obscure. Okay, it's kind of the largest Lie algebra for which we know all of the simple representations, including the infinite dimensional ones. But even in this case, I mean, they're not so easy to describe. Okay, but at least the finite dimensional ones are easy to describe. They're extremely nice, very symmetric, and we've classified them all. Okay, we've done it all from scratch. I mean, we've proved everything. Okay, so where do we go from here? Well, from here, we can use a very important result called Weyl's theorem. There are many theorems of Weyl. This is one of them, which shows that any finite dimensional representation will be a direct sum of simple ones. Okay, and since we know the simple ones, we know the finite dimensional representations in principle. Okay, so this is a very, very important result. If I have a finite dimensional representation, I can always write it as a direct sum of simple representations. Okay, very nice, because then I can, this theorem of Weyl is a general theorem for simple Lie algebras or semi-simple Lie algebras, and the proof is not, I mean, the proof is not, I mean, it's sophisticated and very abstract, but it's not out of this world. But my plan for today is to give you an independent proof of this result just for SL2. Okay, so that we can use some, it's very different from Weyl's proof. Well, it's certainly very different from Weyl's original proof, where he used something called the unitary trick, but very different from a typical proof that I would use in a course on representation theory of Lie algebras. There are essentially two kinds of proofs. There's one which kind of really boils down just to representation theory, but we have to do a lot of fancy things. And there's one where we use cohomology to prove this. Both rely a lot on a lot of structure theory for Lie algebras, so they would be completely beyond the scope of this course. And I think it's interesting to see how we can use techniques from representation theory that are readily accessible to prove this result for SL2. So this is my plan for the rest of the day, for the rest of the lecture. But before I go there, let's capitalize on this result, because, I mean, what I know about the simple representations should be able to tell me something about an arbitrary finite dimensional representation, given this result. Okay, so assuming this result, what can I conclude? Well, remember, so this is classical in Lie theory. So this element h, small h, so this was this matrix, diagonal matrix with 1 and -1 in the diagonal. This element small h, well, generates a one-dimensional space, okay, which is a Lie subalgebra, okay, which we call capital H. With my handwriting, it's not very easy to distinguish small h from this calligraphic h or Gothic H, but well, they're different. So this H, this one-dimensional subalgebra, it's one-dimensional in this case, is very important because we've just shown that on any simple module, this subalgebra will act diagonally with integer eigenvalues which are symmetric. Well, now, if M is an arbitrary finite dimensional module, it's a sum of these simple modules. So the eigenvalues are the same. So I can conclude now that for any finite dimensional simple module, this element H, or if you prefer, this one-dimensional subalgebra calligraphic H, will act diagonally on the module, and the eigenvalues are all integers. Okay, so this decomposes as a direct sum of eigenspaces. That's the first thing that we've found, and these eigenvalues are always integers. Okay, and they're always integers which are displayed symmetrically, like with the simple ones. using the fact that for the simple ones, the eigenvalues, so if m is an eigenvalue, then minus m is also an eigenvalue, okay? This is true for the simple ones, and because of this result of Weyl, it follows that it has to be true for all the finite dimensional modules, okay? So this is very nice, okay? I'll get to this more complicated part here. Okay, so this is all a consequence of our classification and of the theorem of Weyl. Okay, and now a natural question is, okay, I have a module for SL2. I should say, I mean, I didn't go into this because this would further deter us from getting into generalized Weyl algebras, which we would never get to. But I mean, there are a lot of results, even in analysis, in cohomology of some kind of analytic spaces, which use the following trick. I want to prove something, some result like this, okay? Or for example, that there exists a certain kind of eigenvalue, okay? And if you can, if on the space that you're working on, if you can define an action of the Lie algebra SL2, then you can capitalize on this result. If you're able to define an action of SL2, if your space is finite dimensional, then using this result, you know, well, it breaks up into eigenspaces. The eigenspaces are very symmetric. The eigenvalues are integers, and these spaces have kind of symmetrically distributed dimensions. So if in your space you have some non-zero vector here, then you find that there has to be also some non-zero vector here. Okay, and there are a lot of applications of this in combinatorics, in analysis, and so forth. Okay, so this is really powerful. Okay, so as I was saying, a natural question is, okay, I have a representation, a finite dimensional representation of SL2. If I know the eigenvalues for H, well, that's great. I can probably decompose it into sums of irreducibles. I can really. But if I just want to know how many simple submodules does it have? I mean, in the decomposition into simples, how many factors do I have? How many summands do I have? Okay, and this is very easy to calculate because of the following. So if I have a module M, okay, simple. If it's finite dimensional, I know it decomposes into sums of simples. Okay, so let's look at one of the summands, Lm. Well, there are two possibilities for M. Either M is odd or M is even. So we know that the eigenvalues here go from M all the way down to minus M. So if M is even, this has to go through 0. And the weight space corresponding to 0 is one-dimensional. So I capture that vector, which is going to give me one summand. And at the same time, 1 will not be an eigenvalue, because if m is even, the eigenvalues are all even. m minus 2, m minus 4, until I reach minus m. So 0 will appear once with multiplicity once, and 1 will not appear at all. Whereas if m is odd, as I go from m to minus m, I will certainly pass through 1. 1 will be an eigenvalue, okay? And 0 will not be an eigenvalue. And the multiplicity of 1 as an eigenvalue in the simple is also 1. So I just need to count the multiplicity of the eigenvalue 0 and the multiplicity of the eigenvalue 1, and this will tell me exactly how many summands I have. Okay, just do an experiment if you want, and you'll see this right. You'll see this right away. Okay, so this is again another consequence of what we've done. And so, as I said, I mean, if there are no questions at this point, I would like to start proving Weyl's theorem for the case of SL2. Okay, using elementary methods. Okay, so first thing that I need is, I mean, it's a very fine world when everything is diagonalizable, but in general, things are not diagonalizable. So in general, I will need to consider, so if I don't know Weyl's, I mean, if I know Weyl's theorem, then I know that the action of H is diagonalizable because it is on the simple modules, and so it is on an arbitrary finite dimensional module because of Weyl's theorem. But if I don't know Weyl's theorem, I cannot guarantee that. What I can guarantee is, so I have H, the element H, gives me an endomorphism of my finite dimensional module, okay? So I've been representing this endomorphism by capital H, but I mean, I'll stop doing that. So this endomorphism H, so I'll use the same letter for the endomorphism and for the element in the Lie algebra. This endomorphism H determines a characteristic polynomial. Okay, and this characteristic polynomial, since the field is algebraically closed, will break up like this: t minus lambda 1 to the k1, t minus lambda k, so k is better, bad idea, kl to the lambda l to the kl. So this is the characteristic polynomial of the endomorphism H. Okay, so once I have this, this is an elementary fact from linear algebra, I can decompose the vector space, just vector space. I can decompose the vector space into generalized eigenspaces, where by a generalized eigenspace, I mean this. Okay, so vectors which are not necessarily eigenvalues, but so an eigenvalue would mean that h minus lambda acting on m is 0. So this might not be necessarily the case, but if I act with h minus lambda enough times, then I will get 0. You'll see this very well with the Jordan blocks, right? So just as a refresher, if I have a Jordan block here, okay, there's really only, I mean, there's really up to multiples, there's only one eigenvector corresponding to lambda. Okay, the other ones are not. The other elements in this spaces that gave rise to this Jordan block are not eigenvectors. But if to this matrix I subtract lambda, which means that I would get zeros here, and I raise it to a high enough power, I will get 0. And that's essentially this. I mean, this can be proved very easily. I'm sure most of you have seen it in the advanced linear algebra class. Essentially uses Chinese remainder theorem. Okay, so we have these generalized eigenspaces, and in general we'll have to deal with them until we prove Weyl's theorem. Okay, and what I'm claiming is that given a finite dimensional module, there exists some one of these generalized eigenspaces is non-zero, but that's for free, right? Because the module decomposes as a direct sum of generalized eigenspaces. One of them is not 0, okay? So I'm fixing one of those, okay? And also I can assume, so I can take a vector in one of these generalized eigenspaces, and I can assume that this vector is killed by E. I mean, this is not true for any generalized eigenspace, but I can choose one generalized eigenspace where I can choose a vector which is killed by E by the same argument we used before. You take a lambda such that lambda plus 2 is no longer an eigenvector. Okay, is no longer a non-zero generalized eigenspace. So this is true, but my claim is that essentially, as we proved before, but before we were assuming that V0 was an eigenvector. Now I'm just assuming that V0 is a generalized eigenvector, and I can prove the same way that in fact this lambda must be a non-zero scalar, and in fact, using this hypothesis, I will be able to conclude that what I thought was just a generalized eigenvector is really an eigenvector. Okay, so where does this magic come from? Well, it comes from the following. So again, we can take L such that if I act on V0 L times with F, this is still non-zero, but when I act one more time, this is 0. Okay, this is the same argument as before. Because the module is finite dimensional, I'm guaranteed that there exists an integer L with this property. Okay, so now I'm going to use that formula. There was a formula somewhere here, this formula that well, tells me how E and F interact. Okay, so let me use this formula. Where am I? Let me use this formula here. Okay, so let's start with V0. Let's act on it by f to the L plus 1. Of course, I know the result is going to be 0. But let's further act with e to the L plus 1. Okay, and that formula essentially says, I might get it slightly wrong. I mean, there might be a scalar factor that I'm forgetting, but that's not relevant. If I do this using that formula, this will be the sum, okay, going from 0 to L plus 1. H, choose K, we have to see what the hell this means. And then I get f to the L plus 1 minus K, e to the L plus 1 minus K, L plus 1 minus K factorial, L plus 1 minus K factorial, acting on V0. That's what the formula said. Okay, let's worry about the meaning of H, choose K later. Okay, now V0 is killed by E. So all of these terms are going to be 0 except when K is equal to L plus 1. Because when K is equal to L plus 1, then there is actually no E here, and there is actually no F here. That's the only term that could survive, okay? So this is going to give me just one term when K is equal to L plus 1. So this is going to be H, choose L plus 1. This term here is going to be just the identity. This term is just going to be the identity. So this is just V0. Okay, so now I need to reveal what do I mean by this H choose L plus 1. Well, it's exactly as if it were a binomial a number, right? You divide by L plus 1 factorial, and you have H multiplied by H minus 1 up to H minus L, where H is not a number, but it's an operator, okay? Acting on V0. Okay, so now, this element must be 0. So on the one hand, I know that H minus lambda to some K kills V0, but at the same time, I know that H times H minus 1 up to H minus L V0 is also 0. Okay, well, again, using the standard argument, this forces lambda to be one of the integers appearing here. So this is H minus 0, H minus 1, H minus L. So this forces lambda to be one of these numbers, 0, 1, up to L. So I've proved one part of what I wanted to prove, that lambda is in fact a non-negative integer. Okay, but this also forces that. So for example, say imagine that lambda is equal to 1. Okay, this will force, if lambda is equal to 1, these other terms appearing here are contributing nothing to killing V0. So this also means that K, the smallest such K, is actually K equal to 1. Okay, so this I mean, what I'm not saying is just linear algebra. Okay, so just I just realized I need to go a little bit faster. Okay, so this is the first thing we learned. With generalized eigen values are also non-negative integers, and in fact, if they're arising from an element which is killed by E, then in fact the generalized eigenvalues are in fact the generalized eigenvectors are in fact eigenvectors. Okay. Next thing is very simple. I just need to, for those of you not familiar with it, just remind you what a short exact sequence means. It's just a sequence of maps. So there's only one possible map from 0 to M. It's the 0 map. Okay. There's only one possible map from V to 0. It's the 0 map. And exactness means that exactness at a point means that the image of this homomorphism here is equal to the kernel of this homomorphism here. Okay, so for example here, this means, well, the image of this homomorphism is 0. This must be equal to the kernel of this homomorphism. So this means that the kernel of this homomorphism is 0. So it means that the first one is injective. Similarly, the image of this map, the kernel of this map is all of V. And this must be the image of this map. So this map must be surjective. And then here in the middle, it's just the condition that I said. The kernel of this is equal to the image of this. So when you have something like this, this is called a short exact sequence. And I mean, this really means, I mean, I don't like being abstract when I don't need to, but this really means that I can think of W as a submodule of M, and I can think of V as M mod W, up to isomorphism. So that's what it should look like. A short exact sequence just looks like this, okay? I'm mentioning it because, I mean, they're very useful. Technically, I didn't need to mention them, but they're very useful in representation theory, so I'm mentioning them. So what I'm saying is that a short exact sequence of modules like this induces a short exact sequence at the level of vector spaces now. So here, these are modules, here, these are vector spaces, with respect to these generalized eigenspaces. Okay, and this I'll leave it to think about. Unless the action of H on M is diagonal, this would not be true if I replaced eigenspaces with generalized eigenspaces. So this is the reason why I need to do this more complicated construction, okay? Okay, very good. So now let's prove the first meaningful thing, which is at the root of another thing called crystal basis theory, developed by Kashiwara. And which is this claim that I have a module, I choose a non-negative integer, I look at this generalized eigenspace here, I look at this generalized eigenspace here, and I'm claiming that the operator e to the L gives me a vector space isomorphism between these two. We already know that this is true for simple modules, so I need to prove it for any module. Of course, if we knew Weyl's theorem, this is immediate from Weyl's theorem, but we can't use Weyl's theorem because we're proving it, so we need to prove it separately. Okay, how can we do this? Well, induction on the dimension of M. So induct on the dimension of M. Okay, so if M is 0, that's clear. If M is simple, that's also clear because we know that this is true for simple modules. The point is the other cases, okay? So if M is not simple and non-zero, I can choose W, a maximal submodule. Okay, and if I have such a maximal submodule, I have this short exact sequence, this kind of trivial short exact sequence. Well, they all look like this. Okay, and the fact that W is maximal guarantees that this module here is simple. Okay, by maximal submodule, of course, we always mean that it's proper submodule. Okay, now this short exact sequence, as we've seen, induces a short exact sequence. Let me just try to do this kind of quickly. Induces a short exact sequence at the level of generalized weight spaces. I'm just repeating that one here. And by the induction hypothesis, since this module W has smaller dimension, I know that the transformation e to the L here is an isomorphism. This is by the induction hypothesis because W has a smaller dimension. This one is simple, and so, yeah, it's also smaller dimension. So by the induction hypothesis, this is also an isomorphism. Okay, so our point is, what can we say about this map here? Do you think that because its neighbors are isomorphisms, this forces this one to be an isomorphism? And this is true because of something called the snake lemma in representation theory. So it's one of those kind of absurd, for me, I like it. It's usually called abstract nonsense, and I agree with the term. It's by just abstract nonsense, something that I don't value too much, but it's handy. You can conclude that. I mean, I can just show you, for example, very quickly, how would I conclude that this map is injective? So imagine you have this is what I'm going to do is called diagram chasing, if you haven't seen it before. I'm chasing the diagram around. So assume that I have an element here that maps to 0. Okay, this here goes to 0. Well, if this goes to 0, then if I map it here, it's still 0. So this is 0. But since this commutes, this is the same thing as saying that this is 0. Okay, here to here, this is 0. But this map here is an isomorphism. So if I do this and this, and in the end it's 0, it's because it was already 0 here. So this map from here to here, I mean, this element maps to 0 here. Okay, but if it maps to 0 here, and this is a short exact sequence, then it must be in the image of an element here. So this element here, which I was assuming that goes to 0, actually is coming from here. Okay, and so what I have is that this thing here is 0. Okay, but this thing here is 0 means that this thing here is 0. But this is an isomorphism. Okay, so if this thing here is 0, this means that that element here goes here, goes here. This element here is in the kernel of this map. Okay, but this map is injective, so the kernel is 0. So the element on here is 0. So this element here was 0 because this is an isomorphism, and the element that I had initially was the image of this one, which is 0. So this element is 0. So I just proved that the kernel is 0. I think now you understand why this is called abstract nonsense and why this is called diagram chasing. Okay, so we've just proved the result now by induction. This map is an isomorphism. I proved it's injective. It's easier to prove that it's surjective. So we have this. And now this is the final blow, really, to prove Weyl's theorem. How do we do this? So again, we repeat the same argument. So let me just cut. It's again a proof by induction. So I do the same thing as I did before. Okay, I'm proving this by induction on M. Of course, if M is 0, it's a trivial direct sum of simple modules. If M is simple, it's of course a direct sum of simple submodules. So I'm taking W to be a maximal submodule of M, which means that this module here is simple. And since we've already characterized all the simple modules, we know that this module is in fact isomorphic to Lm for some m. Okay? So if this is isomorphic to Lm for some m, so there exists some maximal vector here. So theta in m over w, a maximal vector. This means that I can represent theta as an element m plus w. It's this class in the quotient, and saying that it's a maximal vector means that when I act with E, I get 0, which means that E times M is an element of W. Okay, but since this element theta being a maximal vector doesn't just mean that it's killed by E, it means that it's an eigenvector with eigenvalue, in this case M. Okay, so this theta is an eigenvector with eigenvalue m. So in particular, it's in the generalized eigenspace corresponding to m. So I can assume that this m is in the generalized eigenspace corresponding to m. Okay, so this element E times m is actually in the generalized eigenspace corresponding to m plus 2. Okay, but we know from the previous result that I have this map here from the generalized eigenspace from minus m minus 2 to m plus 2. Okay, I know that the map E to the m plus 2 gives me an isomorphism here. Okay, so this element must be able to form E to the m plus 2 times some vector. Let me call it, well, I didn't want to call it W because I want to call W something else. Well, let's call it V. Okay, for some V in W minus m minus 2. Okay, well, now let me call W this vector here, e to the m plus 1 times v. Okay, the previous one. I don't act so much with e. So what I found out is that e times m is equal to e times w. Okay, for some w, which is necessarily in w m. Okay, so this tells me that if I look at the difference between the two, let's call this element v0 is equal to m minus w. This tells me that E kills V0, okay, and V0 is in the generalized eigenspace associated to the eigenvalue M, because it's the difference of two things which are there, okay? But we just proved that if I have something which is killed by E and it's in a generalized eigenspace, it's in fact in the eigenspace. Okay, so the conclusion is that, oops, sorry, E V0 is equal to 0, and V0 is in fact in the normal eigenspace generated by M, determined by M. Okay, so this shows by a previous result that V0 generates a submodule of M isomorphic to Lm, which was in fact isomorphic to V mod W. Okay, recall this short exact sequence here. Okay, I'm almost done. This is really kind of the point. Okay, we have this short exact sequence here. We have an element here, which I called theta. And I constructed an element here, which I called V0. Okay, by construction, I know that I should have mentioned that the image of V0 under this projection map, that's V0 plus W, that's what? That was M minus W plus W, and W is in W, so this gets absorbed. So this is M plus W, and M plus W is theta. So I constructed an element which, so I started with an element, yeah, you might be confused. I started with an element which mapped to theta. That element might not have suited me because I wanted an element which was killed by E, and I didn't have this guarantee. So using what we've done before, I've replaced it with another one that's killed by E and has the same image, because I modified the original one by an element here, which is in the kernel. Okay, so now I've constructed kind of this correspondence here. And now I can extend this correspondence to give me the whole module, right? Now I can consider the powers fi, and I consider the powers fi. If I want to be really neat, I divide by I factorial. Okay, and we know that here on the right-hand side, these powers, when I goes from 0 up to m, form a basis of this module, because this module is isomorphic to Lm. Okay, and here, these powers will form a basis of the submodule of M generated by V0. Okay, so in fact, again, I don't need to say this in this way, but so that for the people who haven't used this language before, that they see it, I have constructed a map going in the other direction, which I'm calling S. This S is the map from M mod W to M that sends fi over I factorial times theta into fi over I factorial times v0. This is a module isomorphism. Sorry, it's a module homomorphism, which is injective, and it's surjective onto the submodule of M generated by v0, which we know, so the image of S, by a theorem we proved before that the element v0 here, being a maximal vector of weight M, will generate a submodule isomorphic to Lm. Okay, so this map being injective and it makes it an isomorphism onto L. Okay, so this map here is called a splitting in the sense that if I start here, I go in this direction and then I go back in this direction, I get the identity. And when I have a short exact sequence that has a splitting like this tells me that the module in the middle is equal to W. I'm assuming here I have the identity. Otherwise, I would use the image of W under this injective homomorphism. It's equal to W plus the image of S, which is just W plus this module L. Okay, in this particular case, I didn't need to resort to, I know I'm getting a little bit ahead of time. I started a little bit late too, but I mean, I didn't need to resort to the splitting, but I mentioned it for the people who haven't seen it before, and so you know they have access to this language. I mean, we can prove this very easily without any of this abstract stuff. Very simply, noticing that. What is the intersection of these two things? Well, since L is simple, it doesn't have many submodules. So the intersection can be either 0 or L. But if the intersection were L, this would tell me that, that L is contained in W. In particular, it would tell me that this element V0 is in W, and so V0 would get mapped to 0. But no, V0 is mapped to theta, which is a generator of this module. So the intersection of these two things must be trivial. So if the intersection of these two things is trivial and the dimensions match, because as soon as I have a short exact sequence, this tells me that the dimension of this is equal to the dimension of this plus the dimension of this. So as long as these two subspaces intersect trivially, submodules intersect trivially, and the sum of these two dimensions is equal to the dimension of this, which is true, I also would conclude, without using this formality of the splitting, I would also conclude this direct sum. And now we've proved Weyl's theorem by induction because this is a simple module. W is a module of smaller dimensions, so by induction, it's a direct sum of simple modules, and I've just added another simple module to that direct sum. So this concludes the induction, and we proved Weyl's theorem in a way which I think is very elementary. So I think I tried to illustrate techniques of representation theory as I was asked. So I will stop here.